In this video, we will talk about nuclear radiation and the radioactive decay law. Okay. However, we will also talk about how much energy is released in alpha, beta, and gamma decay. We're going to talk about the wavelengths involved when we are dealing with the gamma decay case, etc. So let's recap by mentioning that certain isotopes, and again, isotopes are elements with the same Z, the same atomic number, but different mass number, okay? Or nuclei, or certain nuclei, it's better to say that, or certain nuclei are unstable. We already mentioned that, okay? Which means, meaning they have excess energy which is released in the form of radiation. That was a mouthful, sorry guys. Okay, so by decaying, they get rid of their excess energy, creating more stable nuclei with higher binding energy per nucleon. Okay, so let's go see some examples. Is there anything else I want to mention here? I think not. So let's see some examples. We have the helium isotopes, okay? So helium-3, helium-4, okay? But we also have helium-6 and helium-8, okay? So these are some of the isotopes of helium that are bound, meaning that the protons and neutrons are stuck together. Because you can also have the case of helium-5, but that's not really a bound nucleus in the sense that it lives for like 10 to the negative 23 seconds or something. But these guys live, okay, actually these guys are stable. But the difference is that the B over A is 2.57 MeVs for helium-3, but 7.07 MeVs for helium-4. But then you have helium-6 having 4.88 MeVs of binding energy per nucleon and 3.92 MeVs for helium-8. These guys are unstable, okay? So these are unstable nuclei. I should have quoted their lifetime. We will talk about lifetime in this video. Lifetime is how much time it takes for 63% of unstable nuclei to decay, okay? So the half-life for helium-6 and helium-8, I think is in the order of magnitude of milliseconds, but I don't have it in front of me, so I'm not gonna mention it. Maybe I'm gonna mention it in the description, we will see. So now, these unstable nuclei, helium-6 and helium-8, decay via beta decay, okay? So let's go see the process. So helium-6 decays into lithium-6, and I'm gonna write the the atomic number as well, plus a beta particle that has a mass number of 0 and a charge of -1, plus an electron anti-neutrino, okay? This is something we mentioned in the particle physics videos. Okay, let's go find the mass deficit for this case. So the mass deficit is the mass of helium-6, which is the reactant in this case, minus the mass of 6 lithium, minus the mass of 1 electron, okay? and using their masses found in tables. In an actual exam, this will be given to you. You find 6.0188 atomic mass units minus 6.015 U minus 0.00054 U's. And this yields 0.00326 atomic mass units, which is equivalent to, if we convert it to energy, we find that this is equal to 3.04 MeVs. Okay, so what did we achieve by this Vida decay? We went from a nucleus. I'm going to quote the binding energy. Actually, let me go to a clean page. So the binding energy per nucleon for lithium-6 is equal to 5.33 MeVs, whereas the binding energy per nucleon for 6-helium is, what was it? 4.88. So, as promised, we got something that has a higher binding energy per nucleon, and some energy is released in this Vida decay. By the way, in Vida decay, in general, Vida decay releases about 1 to 10 MeVs from what I remember, okay? So if a calculation is asked for you and you find that in a Vida decay you had something like 200 MeVs, that's wrong, okay? Should be between 1 to 10 MeVs. And let's quickly write down the helium-8 case. Helium-8 decays to lithium-8 plus 1 electron. Actually, let me write it as a Vida particle because this is what the video is about. So Vida 0 minus 1. This guy has 3. And then we have an electron and a neutrino. The binding energy per nucleon for 8 lithium is 5.16 MeVs, whereas the binding energy per nucleon for helium-8 is 3.92. So you see how we also get a higher binding energy per nucleon element by Vida decay. Okay, by mentioning Vida decay and the energies involved and how via Vida decay we get more bound nuclei, I just wanted you to get a taste of why radioactivity occurs, but I'm going to try to go back to the focus of this video, which is radiation in general. So there are 3 types of decays, okay? Alpha, beta, and gamma. And let's now talk about alpha decay, okay? I'm going to keep the discussion about the radioactive decay law for the end. So let's talk about these decays one by one. So alpha decay usually occurs in heavy nuclei. So for high mass numbers, okay? So in this decay, what happens is that you start with a nucleus with some mass number A and some atomic number Z, and you go to, okay, you have an alpha particle plus a new nucleus with a mass number A minus 4 and an atomic number of Z minus 2, because again, A minus 4 plus 4 gives you A, okay? So this should add to that, and now this should add to that, okay? Also, the mass deficit for this decay is the mass of the reactants, and the reactant in this case is the nucleus X that decays, okay? Minus the mass of the product, which is A minus the mass of Y, okay? And the energy involved can be found by delta mc squared, Einstein's relationship. Now, let's see an example, and I'm going to provide some numbers. So, example is the alpha decay of uranium-235, one of the most famous nucleus in nature. due to the fact that it's used in nuclear reactors and bombs. Okay, so it's a popular nucleus. So it releases an alpha particle plus a thorium-231 nucleus. Okay, so 90 plus 2 gives you 92. So these add to that, and 231 plus 4 gives you 235. Okay, the mass deficit is the mass of uranium minus the mass of thorium minus the mass of the alpha particle. Mass of uranium is 235.04 U, and again, in a scenario where they ask you to find this, they will provide the masses. Okay, you don't have to remember that. Minus the mass of the thorium, 231.03, minus the mass of the alpha particle, which is, we will take as 4U. So we get 0.01 U, which translates to, actually, let me bring this down here. Okay, delta MC squared gives me 9.33 MeVs. Okay, now some facts or trivia about alpha decay. So alpha decay releases about 8, actually let me write 5 to 10 MeVs of energy for almost across all alpha decays that can occur. Alpha radiation is dangerous and highly ionizing. So it's a dangerous and highly ionizing radiation. This is due to its mass, because it's heavy, and it also has twice the charge of an electron, but in the positive sense. Okay, so it's dangerous, but when we say dangerous, it's dangerous inside the human body. Okay, it's inside the human body. It's dangerous because it can break DNA or other molecules and cause cancer. Okay, but outside the body, it can be blocked. It can be blocked by skin or a thin paper. Okay, this is because it's heavy, and it also has a large amount of charge, so it can easily be stopped by atomic electrons inside material, pretty much. Okay, and so it's harmless. So harmless outside the body. Okay. Also, let me mention this. It can be stopped by a few, something like 2 to 3 centimeters of air. Okay. The next type of radiation is Vita radiation. Okay, so Vita decay is what we will discuss now. We already discussed that in the introduction of the video, like in the first few minutes, because we gave it as an example. But let's write a few more things. So there are two types, actually, two types of Vita decay. We can have the Vita minus and Vita plus. Okay, so a nucleus can emit an electron or a positron. Okay, it's observed in any nucleus. I mean, both low mass number and high mass number. Okay, unlike the alpha decay, which is mainly observed in really heavy nuclei. Okay, except one case, which is beryllium 8, but it's just one case, I think. So, so two types. It can be observed in any type of nucleus, but usually it's observed in proton or neutron-rich nuclei. So, and we already saw one example. So helium-8, for example, is a neutron-rich nucleus because it has 2 protons but 6 neutrons. Okay, that's a lot of neutrons compared to protons. So that's a neutron-rich nucleus. Okay, let's write down what's the types of reactions that can happen. So actually, I'm not gonna use this dash. So if you have a nucleus X with mass number A and atomic number Z, it can go into a nucleus Y with the same mass number. It's important to remember, but an atomic number increased by 1 plus a beta particle, a negative beta particle, plus an electron antineutrino. Okay, so you see how this plus that adds to that, and then this plus 0 gives you the mass number that you start with. And for the beta plus decay, you start with a nucleus X and mass number A and Z, and you go to a nucleus, let's call it Z, with mass number A again, and now an atomic number reduced by 1, okay, because you emit a beta plus particle, okay, plus an electron neutrino. Hope this makes sense, because Z minus 1 plus 1 gives you Z, okay? So beta decay does not change the mass number. It's important to remember, guys, okay? But it does change the atomic number. And as we saw in the videos related to particle physics, beta decay is the only way that exists. It's the only mechanism, if you will, that exists in nature that allows for the transformation of elements from one to another. Okay, I mean, it's a naturally occurring thing because you can artificially do that using accelerators, but in nature this happens via beta decay. The underlying this is for trivia, but it's good to know the underlying mechanism for beta decay. Actually, the underlying mechanisms for beta decays are the decay of the neutron. This releases an electron, right? And the decay of the proton. The proton does not really decay. It's a bad term. This second decay, the beta plus that releases a positron, can only happen inside nuclei, okay? Because in nature, the proton does not decay into a neutron because the neutron is heavier, so it doesn't make sense. So only in the nuclear environment does this reaction happen, okay? I hope this makes sense. If it doesn't, ask me in the comments and I will provide more details if you want, sorry. Now let's see examples. We already saw 2 examples with helium-6 and helium-8 in the beginning of the video. Let's talk about a very popular element, carbon-14. You hear about it all the time when it comes to studying past environments and dinosaurs and such. And not dinosaurs, sorry, that was a stupid thing to mention because dinosaurs are millions of years old. When you deal with archaeology, like things that happened about 3,000 to 5,000 years ago, they use carbon-14 to date skeletons and stuff like that. So carbon-14 decays into nitrogen-14. You see, the mass number does not change, but we get an element with a higher atomic number, plus beta, plus an electron antineutrino. Another example is magnesium-23 with atomic number 12. And now this is beta plus decay. Goes into sodium-23 plus a beta plus particle plus an electron neutrino. Okay? We already saw examples where we calculated the energy released in these reactions. By the way, let me go up here and mention that delta M, the energy deficit, is equal to the mass of X minus the mass of Y minus the mass of the electron in the case of beta minus decay. And for the beta plus, we have mass of X minus mass of Z minus mass of the electron for the beta plus, okay? And then using delta MC squared, you can find the energy released. But we already covered that in in the beginning of the video, so let's move on. Now, about Vida radiation, inside the body, let's start with that, inside the human body, and I guess any other animal's body, it has a medium penetration and ionization, but still, it's not something good to have inside you. But still, exposure must be minimized, okay? Since Vida particles, Vida radiation consists of electrons, they carry a charge of 1, like -1, and they are really light, so they can still destroy molecules and change molecules, etc., but it's not as dangerous as the alpha particle, okay? But still, it's not something good to get exposed to, okay? Outside the body, it can be stopped by several centimeters of air. Usually 10 to 15 centimeters, if I'm not mistaken. Or it can be stopped by a thin aluminum sheet. So, for Vida particles, you cannot use a thin piece of paper and stop Vida radiation. It will go through. So you need something heavier, like aluminum, okay? It's thicker, it has a higher density, so you need something like that to shield from Vida radiation, okay? The uses of Vida radiation is, let's mention a few uses. So it's used for tracing. For example, you can put it in blood and then detect where in the body this Vida tracer goes and stuff like that. It can be used for medical treatments, like for cancer, etc. Okay, now this is all I want to mention about Vida particles, I guess. Let's now talk about gamma decay. Okay, so gamma decay. It can be observed in all nuclei, in all types of nuclei. It's better to say that. I mean, low and high mass number, okay? But it can only be observed under certain circumstances. And let's see an example. Remember the carbon-14 decay that goes through, that decays via Vida radiation? Actually, there is an intermediate step. So, and the intermediate step is that you have the production of nitrogen plus a Vida particle plus an electron anti-neutrino. But usually, in these types of decays, I put an asterisk there because this means that this nitrogen is in an excited state, okay? And that excited state, in an excited state in the same sense that when you have an atom, for example, you can promote an electron to a higher state, and then the electron comes back to the ground state by emitting photons. So it's the same case with nuclear physics. So this nitrogen is produced in an excited state, which de-excites by emitting a gamma particle, okay, which is nothing else than a photon. So in general, actually, let's do one more example. Nickel 60 M. This M means a metastable state. So nickel 60 can exist in a state that is a little bit excited with respect to the ground state. And this nucleus can decay into nickel 60 and emit a photon, okay? And again, by excited state, we mean exactly the same thing as we mean in atoms when you have an excited state when an electron is promoted to a different energy level than the ground level, okay? So let's write down that in general, you have a nucleus with some mass number A and some atomic number Z, which is in an excited state, and it decays into itself pretty much, but in the ground state plus a gamma particle. Okay. Now, in terms of an example of how much energy is involved, let's see cobalt-60. So cobalt-60 with atomic number 27 decays to nickel, but in an excited state, 6028, by emitting a beta particle and an anti-neutrino. Now this guy though is in an excited state, so it decays to nickel-60 in the ground state plus a gamma particle, and the energy of the gamma particle is 1.33 MeVs, okay? So that's a lot of energy pretty much. This is how energetic gamma particles are. So gamma decay usually involves energies of photons of the order of magnitude of 1 to 3 MeVs, okay? So I'm gonna write this down. So gamma particles have energies of about 1 to 3 MeVs. Now let's see how much what the wavelength of this gamma ray is. So recall that for photons, and this is what gamma radiation is, the energy is given by the Planck's constant times the frequency. But then the frequency is equal to the speed of light over lambda. So lambda can be found by solving h times the speed of light over the energy. And if we plug in numbers, we find 3 times 10 to the 8 is the speed of light, and then 1.33 MeVs, which is 10 to the 6 times 1.6 times 10 to the negative 19. We find 9.35 times 10 to the negative 13 meters. So that's a really, really small wavelength, guys, okay? So gamma particles have really small wavelengths or equivalently very high frequencies, okay? Now, some of the properties of gamma radiation is that gamma radiation has low ionization potential, both inside and outside the body, because nothing outside the body, sorry, because nothing than light, right? But nevertheless, long-term exposure is dangerous. Just because it's not highly ionizing, it doesn't mean that you have to sleep with a gamma radiation source under your pillow, okay? This is what I mean. It's very penetrative. So it's very penetrative. Only thick lead or concrete can stop it. Okay, but usually lead is used, okay? It can be used as a tracer, just like beta particles, or for cancer treatments. By the way, can I do that and get things deleted? No. Okay, that's it for gamma decay. Let's now talk about one more thing. Actually, yes, that's the last thing I want to talk about before we talk about the radioactive decay law. So another thing that happens in nature is what is called the decay chains. Okay, decay chains. And what I mean by that is that maybe you start with uranium-235, which, as we saw, decays to an alpha particle plus thorium 231 90. But thorium is also unstable, and let me go to the left here, and it also decays to palladium 231 91. So this is a beta decay. And then palladium is also radioactive. It's unstable. So it decays to AC, I think it's called actinium, something like that. 227 89. So this is an alpha decay now, plus alpha. And there is a whole cycle of these things. So it's called a chain because you start with one nucleus and you keep going until you reach. So I'm going to put dot, 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 because many other reactions happen until you reach radon. Radon 21986. This is the gas I mentioned, I think in this video. Maybe it was in the previous video about nuclear physics. This is a dangerous noble gas that is also radioactive. So I'm not going to write it here. It's also radioactive, and it should be removed from your environment. So this is what the decay chain is. You start with an unstable nucleus, which decays to another unstable nucleus, that decays to another unstable nucleus, and so on and so forth. Both alpha and beta decays might be involved, as well as gamma decays. Okay? So I'm going to provide a small summary before moving on to radioactive decay law, to the radioactive decay law. So the summary is that some nuclei decay. There is alpha, beta, and gamma radiation. Alpha decay is dangerous. Thin paper can't shield it. Beta radiation is less dangerous, but still, so I'm gonna write medium dangerous, something like that. Aluminum can't shield it. And gamma is the least dangerous, so low danger, okay? Yes, and now let's proceed to talking about the time involved for these decays. Now, let's talk about the radioactive decay law, and let's start by saying that the probability that an unstable nucleus will decay in the next second is lambda. Okay, lambda is called the decay constant, and it has units of seconds to the minus 1. Okay, the nucleus that will decay is random. So if you start with 100 radioactive nuclei, which nucleus is going to decay first is random. Okay, it decays spontaneously. Okay, so the nucleus that will decay is random. It will decay spontaneously. And each nucleus is independent, meaning that if I am nucleus 3 and I decay, that will not affect when nucleus 50 is going to decay in the same example of 100 unstable nuclei. Okay, A is a larger lambda means a higher probability sorry, cannot write English, so probability that the nucleus will decay in the next second. Okay, let's write down a few examples. By the way, this lambda refers to any type of radiation. It can be gamma, it can be alpha, it can be beta radiation. Okay, so oxygen 24 has a lambda of 9.63 seconds to the minus 1. Okay, carbon 16 has a lambda of 0.93 seconds to the minus 1. Carbon 14 has a lambda of 3.86 times 10 to the negative 12 seconds to the minus 1. And uranium-238 has a lambda of 4.92 times 10 to the negative 18 seconds to the minus 1. If you ignore seconds to the minus 1 for a moment, you see that the highest lambda is for oxygen 24. So there is a high probability that this nucleus decays. Okay, so it's going to happen faster. Whereas for uranium-238, lambda is roughly 5 times 10 to the negative 18, so it's almost 0. So that's a nucleus that decays slowly. And we're gonna discuss this later, but for now, let's also write down that the half-life, which is written like that, T1 half, is equal to ln of 2 over lambda. Okay, so if we go use this, with this lambda, we will find that the half-life is 72 milliseconds, and the half-life is the time needed for half the nuclei to decay. Okay, so for oxygen 24, this half-life is 72 milliseconds. For carbon 16 is 0.75 seconds, so slower. For carbon 14, it's 5,700 years, which gives you a clue why it's used for radioactive dating of skeletons, human skeletons. And T1 half for uranium-238 is 4.47 times 10 to the 9 years. So it takes 5 billion years almost for half of uranium-238 to be gone. So that's a really slow process, okay? And that's roughly the age of the Earth. And that's how the age of the Earth was actually determined back in the day. But that's not something you need to know for now. So, since we already mentioned half-life, let's continue. So with half-life, so T1 half is called the half-life. So let's define this. It's the time needed for half the nuclei in a sample to decay. So if we start with N naught, where N naught is the number of radioactive nuclei, so maybe it's 100. In one half-life, half of them will be gone, okay? So we'll be left with N naught over 2. In another half-life, one half of one half is going to be gone, so we will be left with N naught over 4, right? Then in another half-life, T1 half, another one half of one half, so 1/8 will, sorry about that. Okay, so N naught over 8 will remain, and so on and so forth. So we lose half the nuclei in each half-life. Now, if we plot these findings in a plot where we have the number of nuclei, N naught in the vertical axis. So the units for the vertical axis are N naught. So that's N naught. This is N naught over 2. This is now N naught over 1/4 of N naught. And here you have 1/8 of N naught. And then if we put on the horizontal axis the time in units of half-lives, so 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, and if we plot this thing, so in 1 half-life, this is wrong. So at time 0, we have all nuclei in our sample. After one half-life, we are left with n naught over 2, half the nuclei. In another half-life, we are left with even less, and then in another half-life, we are left with even less, and so on and so forth. So if we draw this line, we get the exponential decay line, okay? So for decays, we get the exponential decay curve. So let me use black. Exponential decay curve for alpha, beta, and gamma decay represents the random nature of radioactive decay. Now, how many nuclei will decay per second depends on the number of nuclei and it's called activity, denoted by A. Okay, so this is important. Activity is measured in seconds to the -1 or becquerels, BQ. Okay, so what I'm trying to say is that if A is the number of nuclei that decay per second, that's going to be proportional to the number of nuclei, okay? And the proportionality constant is lambda, the probability that the nucleus decays per second. And the negative sign is because, the minus sign is because the number of nuclei reduces. The number of nuclei reduces. So, since by definition A is the number of nuclei that decay per second, then this is given by dn over dt in seconds to the -1. Okay, so we can use, let's call this equation 1 and let's call this equation 2. From 1 and 2, we find that dn over dt is minus lambda n. Okay, so we can integrate this. Okay, this is a simple differential equation. We can integrate, I make this a dummy variable, and I integrate from n naught to n, and this is equal to minus lambda dt, and I make a dt prime a dummy variable. So for time 0, we have n naught nuclei, and for time t, we have n nuclei, okay? So if I integrate dn over n, dn prime over n prime, I get the ln of n prime from n naught to n equal to minus lambda t prime from 0 to t. So ln of n minus ln of n naught is minus lambda t pretty much. And using log identities, I can bring this into the form ln of n over n naught equal to minus lambda t. So n is n naught e to the minus lambda t. And this is the radioactive decay law, guys. And we actually proved it. Okay, that's cool, I hope. Now remember that activity A is defined as dn over dt, right? It's the rate with which nuclei decay in units of becquerel, which is inverse seconds, right? So, since we already found the law of radioactive decay, we can take the first derivative pretty much. So we have d over dt of n naught e to the minus lambda t. And then we see that we get, what do we get? Minus lambda n naught e to the minus lambda t. And we can define this as the activity at time 0, okay, a naught. So we see that activity is also following the radioactive decay law, okay? So whatever is true about activity, the number of nuclei is true about the rate with which the nuclei decay, okay? And before we move on, we can also prove another thing. So note the number of nuclei, in some quantity, in some, actually it's better to say in some amount of mass, m, measured in kilograms, is, so n, the number of nuclei, is equal to the mass over the molar mass of that material times Avogadro's number. We don't need to prove this, but let me write here that mr is the molar mass in units of grams per mole, and Na is the well-known quantity of Avogadro's number, which is 6.022 times 10 to the 23rd particles per mole. So you see that this is a unitless quantity. So m is, sorry, let me write it this way. So mass over molar mass over times Avogadro's number. In terms of unit, this is what the brackets means, is kilograms over kilograms per mole times mole to the minus 1. So indeed, this is a unitless quantity, which is the number of nuclei. But anyway, I'm mentioning all these because the mass is also following the exponential decay law. Okay? It's very rarely used though, okay? Because usually what happens is that maybe you have some quantity of, let's say, uranium-235 in a block of metal, okay? So the mass of that block is, I don't know, 10 kilograms, from which 10 grams are uranium-235. So after uranium-235 is decayed, you will still have the 10 kilograms of the block, but the amount of uranium will be 5 grams, for example. So 5 grams will turn into another metal. So it's very rarely used, but I just felt that I mentioned this. Now let's see an example. Okay. So for carbon-14, lambda, the decay constant, is 3.86 times 10 to the negative 12 seconds to minus 1. What is the activity of 1 kilogram of carbon-14? Okay, and to solve this, you need the molar mass, which is equal to 14.0032 atomic mass units, which is equivalent to 14.0032 grams per mole. Okay, so the activity is given by lambda times n. So lambda is given 3.86 times 10 to the negative 12, and then we are given 1 kilogram. So we have to find n. We have to use this formula here, pretty much this one. So the mass is 1 kilogram. Actually, let me keep the red color. So we have 1 kilogram. We have to divide this with 14.0032. And then we have to remember that 1 gram is 10 to the minus 3 kilograms per mole, right? Times Avogadro's number, 6.022 times 10 to the 23 moles to the minus 1. These moles with these moles cancel. These kilograms with these kilograms cancels. And we find, let me go back to black color, 1.66 times 10 to the 14 becquerels. Okay. It's not necessary to remember, but usually the molar mass is the atomic the atomic number times grams per mole. So for carbon 14, the molar mass is about 14 grams per mole. This is what I mean, okay? For water, H2O, the molar mass is going to be 18 grams per mole, and so on and so forth. How do I know it's 18 grams per mole? It's because water has 2 hydrogen atoms that have a mass number of 1, so 2 times 1 is 2, plus 16, which is the mass number of oxygen, 18, so 18 grams per mole is the molar mass of water, okay? So this is from chemistry, but it's good knowledge to have in the back of your mind when you work your way through an A-level test. Now, let's talk about the time constant, which is something we haven't mentioned yet. So T is tau, actually. It's a Greek letter. It's the Greek tau, okay? Is equal to 1 over lambda. So the time constant is the inverse of the decay constant. So tau is the time constant, okay? And since lambda has units of inverse seconds, the inverse of lambda has units of seconds, okay? So in units of seconds. So n is also given by the formula n equals to n naught e to the minus t over the time constant, okay? So that's another form of this equation. Now, something important here is that in one time constant tau, n is equal to n naught e to the minus tau over tau. So we get n naught over e, which is equal to n naught over 2.71, which gives us 0.37 n naught. So in one lifetime, time constant, 63% of nuclei decay. Okay, so this is similar to the capacitor case. We saw the time constant for capacitors, and it's also an exponential decay curve. So the same thing applies to nuclear decay. Now, we already talked about it, but the half-life is the time needed for 1/2 of the nuclei to decay. So if we go back to the n equals to n naught e to the minus t over tau law and replace, we find n naught over 2 is equal to n naught e to the minus the time needed for 1/2 of the nuclei to be gone over tau. So this cancels, and we are left with t 1/2 equal to tau times ln of 2, which is equivalent to ln of 2 over lambda, which is something we already saw. Okay, I skipped a step here, so the way to find this is to do 1/2 equal to 1 over e to the t 1/2 over tau, and then cross multiply e to the t 1/2 over tau is 2, and then take the ln of both sides to find t 1/2 over tau is ln of 2, so t 1/2 is tau ln of 2. Okay. Okay, a few more things are left to be discussed. Let's talk about log curves. Okay, since n is n naught e to the minus lambda t, and the same goes or a equals to a naught e to the minus lambda t, notice that if we take the log of both sides, if we take the ln in both sides, we get ln of n equals to ln of n naught minus lambda t, okay? And this is an equation that has the form y equals to c plus mx, okay? So t is x, ln of n is y, the constant c is ln of n naught, and the gradient of this curve is minus lambda. So if I plot this, if we plot this, we get, so if we plot ln of, let's say, A in Becker over Becquerels, we will find, let me erase this, make some space. So if we plot this, okay, and in this axis we have ln of A, for example, in units of Becquerels, and we have time, we get a straight line, okay? And the gradient of this line is minus lambda. And the y-intercept is ln of A naught. And why am I mentioning A naught? Because activity follows exactly the same line, okay? So the gradient of this curve will give you the time constant, and the y-intercept will give you ln of A naught, or ln of N naught if you have the curve related to the number of nuclei. Okay, now I want to say a few words about measuring radiation. It's very rarely tested, but I want to mention it anyway for completeness. So measuring radiation. So to measure radiation, to study radiation, to study this decay law, pretty much, we usually choose gamma radiation to study nuclear decay, okay? Because it's not easily absorbed by the environment, okay? So your results will be exact. This is what I mean, because it's not absorbed. So there is something called the radiation law, and I'm gonna try to make a scheme to show you what I mean. So if we have a source of radiation, it emits, let me use orange. So this is my source. It contains a radioactive nucleus, okay? So this is the source containing a radioactive nucleus that gives off gamma rays in the space around it, okay? But this radiation is spread in a sphere, pretty much, right? If you imagine it in space, the radiation spreads in a sphere around the source, just like the sun is a source of radiation, pretty much, right? And it emits radiation radially away from it. It's the same with radioactive sources. Okay, so if I put a detector now that has some window, okay, so this is the window of detector, and the detector is cylindrical, something like this. So this might be a Geiger-Muller tube, for example, Geiger-Muller tube, okay? And this is connected to some counter that tells you, okay, so this is a counter that tells you how many particles are detected per second. Then the radiation received by the Geiger-Muller tube is given by measured amount of radiation over total is equal to the area of this window, pretty much, so this area, over 4 pi r squared, where r is the distance from the source to the window. I hope this makes sense, but let me write down that radiation is emitted in a 4 pi r squared sphere, okay? So only radiation captured, actually passing, not captured, passing, oops, radiation passing through the window is detected. So what I mean, again, is that let's say that I have a source. Okay, maybe this will make it more clear. So I have a source, and this is a sphere, and maybe I put my detector up here, or maybe actually, okay, let's put the detector there. So this is the detector A with surface area A, and I made it orthogonal this time. Let me draw the sphere again. For some reason it disappeared. Okay, so this is the source, this is the window of radius A, and this is the distance from the source to the detector. So all this radiation here is lost, right? And only radiation that passes through the window is detected. I hope this makes sense. Okay, let's try to see an example. So a Geiger-Müller tube with area 10 square centimeters is placed 10 centimeters away from a gamma source. The background radiation is 10 becquerels. So the 10 becquerels means 10 counts per second, okay? And the measured radiation by the counter, is 1000 becquerels. What is the activity of the source? So to find this, again, we have to go and apply this formula. Measured radiation over the total radiation is equal to the area of the window of the detector over 4 pi r squared, where r is the distance from the source to the counter. Okay, now we are given the measured radiation as 1000 becquerels, but we have to subtract the background radiation. All right, and then what do we mean by total radiation? Total radiation is the activity of the source itself. Okay, so if this source is emitting, I don't know, 1 billion counts per second, only those counts that go through the window will be measured, will be captured. Okay, so 1000, which is the radiation detected, minus 10, which is the background radiation that we have to subtract, over the activity of the source, A naught, must be equal to 10 centimeters squared, which is the window, the area of the window of the detector, over 4 pi times 100 squared centimeters squared, which is the distance from the source to the counter. So if we solve this, we find that the activity of the source is actually 124.4 times 10 to the third becquerels. So from all this activity, only 1000 counts per second go through the window. So I hope this makes sense. This completes the nuclear decay topic of Unit 5. I hope you guys find these videos useful. Let me know in the comments how I am doing. Please like and subscribe, as other YouTubers say. I'm not a YouTuber, but I hope these videos are useful.